VLSos here. This is a video lesson on the derivative of a beast, which means taking the derivative of a complicated expression that uses lots of properties within it. This one has taken me down before. This is my second attempt. Let's take a look at an expression, the inverse of sine of y times 87 to the cosine of x all over 2 times the natural log of the secant of y to the fourth. Lots going on. If we had a property for differentiating a beast like this, it would be use technology. But we need to be able to do something like this by hand, and this lesson is mostly an example of how to organize a complicated solution process. This function we could be asked, or this expression we could be asked, what is the derivative with respect to x? And the first thing to do is to take a look at the general structure of what we need to differentiate. It's a rational function, a function divided by another. And this function, if it's rational, is going to need the quotient rule for differentiation, which is a good thing to remind us on our paper that we're going to use the derivative of f over g is the derivative of f, or the derivative of the numerator, times the denominator minus the numerator times the derivative of the denominator all over the square of the denominator. And in reminding us of the rule for the derivative of a quotient, we have chosen letters to represent the pieces of the original expression. In this case, I've chosen f to represent the numerator, and if I have, I'm going to write what I have assigned to bf on its own line of work. And as we progress through taking the derivative of this, it's going to create many pieces. I'm going to use many variables and symbols to represent those pieces. And each time I do, I'm going to list it independent of the rest so that I can collect the pieces at the end and assemble the derivative. My g function then is chosen to be the denominator, 2 times the natural log of the secant of y to the fourth. And I take a look at the f and g pieces. They themselves are complicated functions. F is the product of inverse sine and an exponential function. And the exponential function is composed with a cosine function. Also, it's worth noting that I've got two variables here, y and x. So if I'm taking the derivative with respect to x, I need to treat y as a function of x and apply a chain rule as we do when we differentiate implicitly. The structure of the f function is the product of two functions. So I'm going to choose two new letters to represent those pieces, in this case h and j, and remind us then that the product of two functions, or the derivative of a product of two functions, is the derivative of the first factor times the second plus the first times the derivative of the second. And in so doing and reminding the structure of that piece of the derivative, I've assigned h and j to be functions in themselves. H, I'm going to call the first factor of this product inverse sine of y. J is the exponential 87 to the cosine of x. These pieces, h and j, are relatively simple. H is a composite function, or is going to be treated as such because it's the inverse function composed with y, which we're treating as a function of x. But it's simple enough now that I can list the derivative of h is going to be the derivative of inverse sine composed with y. The derivative of inverse sine is, some people have memorized, not likely, so looking in a derivative table is often necessary when using these uncommon functions. The derivative of inverse sine is 1 over 1 plus its input squared, in this case y squared. And then we're going to apply a chain rule to multiply by the derivative of y with respects to x, because our original expression is being derived with respects to x. The j function is an exponential composed with cosine, so we'll apply a chain rule, but we don't need to apply a second chain rule because x is the variable that we're differentiating with respects to. So the derivative of j is 87 times the cosine of x times the natural log of the base 87. That's using the property for the derivative of an exponential. And now we apply the chain rule, multiplying by what is composing that exponential function, and the derivative of cosine is negative sine, using parentheses to isolate that negative. So I have the pieces h and j and their derivatives to construct the derivative of the f function. I'm going to take a look at g. G is a composite function, and it's the y function inside of the power of 4 function, inside of the secant function, inside of the natural log function, which is also being multiplied by the constant 2. So if we're going to have a structure for g, it would be a constant, in this case I'm going to use the letter k to represent the constant, times a function, the natural log function, but we're going to give that a letter. I'm going to use Greek letters now for my functions. We're going to call the natural log function alpha, and alpha is composed with another function, secant, which I'm going to assign the letter beta to represent, and that is composed with the fourth power function. I'm going to skip over gamma and delta and use the next Greek letter epsilon. And epsilon is the fourth power function that is composed with y. So I've used Greek letters because I've used many letters so far. And when I use Greek letters to represent things, I often use alpha and beta. I skip gamma because it looks very much like alpha. And delta I skip because delta often represents change in, and so I skip over that. I also don't use theta because it's so common with angle measures. So these functions that I've chosen now are going to be listed independently as independent pieces. The alpha function is the natural log, and because it's a simple piece, I can list the derivative of alpha right away. The derivative of natural log is 1 over x. The beta function was assigned to be secant, and the derivative of the secant function is secant tangent. The epsilon function is the fourth power function, and its derivative is 4x cubed. Y is being treated as a function of x. So I could check. I've got the pieces now listed for the g function, and the f function. I can now construct their derivatives from these pieces. The f function is a product rule, so the derivative of f is going to be the derivative of h times j plus h times the derivative of j. The derivative of g is ready to go. This is probably the most challenging part of the solution process. We have the structure here. The derivative is going to be several chains. But every time I take a derivative of an outside function, I have to remember to compose it with the original functions. So we have the constant 2, which could have been part of my list. Appropriate place to put it. The derivative of g would be that constant times the derivative of the alpha function, where its input is composed with beta composed with epsilon composed with y. So that's going to be 1 over the beta function composed with the epsilon function, which is composed of y. Then we chain the derivative of the beta function composed with epsilon composed with y. So the derivative of the beta function is secant, and its input is epsilon composed with y, times the tangent of its input, which is epsilon composed with y. That was the chain of beta. Now we multiply or chain the derivative of epsilon, which is composed of y. And finally, we chain the dy over dx, thinking of y as a function of x. I have the derivative for f and the derivative for g, which completes the pieces that I'll need to make the structure of the derivative with f and g as well. So the derivative of the original expression is, beginning with the derivative of f times g. And because this is a binomial, I'm going to put it in its own parentheses. We're multiplying by g. Minus the f function times the derivative of g getting stuffy all over the square of g. I hope I got it right.